Morning. Well, afternoon, I think.
Yeah, good afternoon. Buddy, everyone's coming in right now, but welcome. We're the last day of November here, coming back from break. Welcome, everybody. Hope y'all had a restful, break and relax a bit. I'm hoping. All right, let's jump into our check-in question, and then we can see who's here, who's missing, and so forth. Let's see. Okay. Okay, I think this was kind of like a Halloweenish question from last time, but we could still use it. Would you ever go to a graveyard at night? Go ahead and put whether or not you would, as I'm letting more of us in. I'll check out what y'all are saying. All right, let's see. We've got a bunch. All right, we've got yeah, maybe, nope, yes, nope, no. Wow, it's like 50-50 right now. I have before. Oh, okay, Ryan. Yes. With people, yes. Yes. If I'm not alone, no. Yes. Haunted or not, I'm I'm turning into Ghostbusters 2.0. Awesome. Then we have no. So far it's 50-50. I mean, I would go if I had friends, but I have no reason to, so right? All right. Cool. And as far as if anyone's wondering if I go, yes, I'd go. I go alone or with friends. If they're open, they're not open at night though. They close like at 5 p.m. or something. So I would totally, especially because I guess I'm not really superstitious. I totally would feel calm walking through a cemetery, but that's just me. All right, cool. So let's go ahead and see who we don't have present. So I don't have Jalen. Let me know if that's true. Jalen, I'm missing Jalen. I'm missing Denise, Gerardo, Brandon, Miles Ford, Alex, Carlos, Kyla, AJ. Am I really missing AJ? Yeah, I'm missing AJ. Risha, Leon, Marcella, and Celia. So if I said someone's name and they're your friend, if you could please send them a text to come on in. We definitely don't want to be late coming back to class because then we're going to be lost, coming back in tomorrow. So yeah, that's who we have absent. I'm gonna also kind of just quickly send a remind just so I could get everybody in more. Cool. All right, cool. So let's go ahead and jump into what we're doing today, y'all. Yep, it's been a week. But then again, there's times, yay, we got Alex. There's been times where, we don't see each other for 3 weeks, but we jump right into it. Oh, and we got Gerardo. Yes. Yay. So we're getting a few more people. Gerardo, we got Alex. Awesome. We're getting more. And yeah, by the way, I sent a reminder to everyone. So if you got a text, sorry about that. It was hard to kind of just, we have about like 8 students or so that are missing. And it was a little bit hard to the time to find those 8. Yay, we got Jalen. All right. Thank you all. Thank you for texting your friends. So what's the title? Gonna be right here. If you look at number 2, we're gonna be talking about right Riemann sums today. So our agenda, we just had our attendance and check-in question. Some of you just came in, so happy that you're here, you made it. We're gonna be jumping right back into the Riemann sums. We left off with that on Thursday, right before our break. We talked about the left Riemann sum. Now we're gonna talk about the right. Then we have a bunch of participation today. You wanna make sure that you put your name and get your credit today as I built in these check points for us. And so 2 participation points. We're going to look at what makes a good approximation, and then we're going to have a checkout. Asynchronous number 13 is due tomorrow. It says tonight. It's due tomorrow, Tuesday. And my office hours for everybody, especially if you're struggling, right? My office hours always Monday through Wednesday at 10, especially too if you're missing any async work, because I'm happy to walk you through it. I'm happy to also, like, let's say you're one of the students who has like a pile of asynchronous work and you're overwhelmed. I'm happy for you to come on in, and then we could kind of identify what are important ones to do so you don't feel so overwhelmed. So that's just, some help I could provide you. Definitely take advantage of that. Welcome for those that just came in. Let me just double check. We just got Kyla in, and who else just came in? Someone just came in. I want to make sure I mark you here. And AJ, yay! Thank you so much for being here, y'all. AJ's here, and then we just got Leon as well. Great! I'm so happy y'all made it in. Okay, so there's our agenda. Before we jump into our notes, yes, you want to have your notebook open and ready, or if you're writing your notes on a Google Doc, go ahead and have that ready. Either one, just be prepared to write notes. Before we jump into today's notes, though, I'm going to recap as usual because we should have a little bit of a reminder of what we did. So right before we jumped into the Thanksgiving break, we were talking about how to approximate the area under a function using Riemann sums. Riemann sums are those rectangles we were drawing under the curve. And when we find the area of the total of those rectangles, we kind of create an estimate of the total area under the curve. It's not perfect though, because there's going to be like white space under it. And as another recap, before we learned about Riemann sums, you all tried on your own on the Desmos activity to estimate the area. And these were the different things y'all did. So if you look at this bottom poster, they did like sideways rectangles to estimate the area. This one right here almost looks like Riemann sums, except they like kind of chopped it up like so, and they tried to kind of reflect it up. And as a reminder, whenever you have your units, like in this case right here, beats per minute times minute, the area does represent something. And how you figure out what the area of the curve represents is all you got to do is you take the rate times time. This is just review. No, you don't have to write this one down. This is just review. Our big idea is rate times time equals accumulated unit. So for example, when you had this beats per minute graph, your rate would be the y-axis. It's beats per min. This is review. You don't have to write this down right now. This is me reviewing what we just, talked about before we jumped into Thanksgiving break. In this case, it's beats per min. That's your y-axis times your time is your x-axis. That's minutes. And we realize that when you multiply rate times time, the unit cancels out. So in this case, minutes does, and you're left over with beats. So in this scenario, because we were given units, the area under the curve, once you calculate it, would represent the number of beats over that 10-minute interval that person was doing yoga. So that's just a review, estimating areas under curve and what they mean. Clear my drawings. Yay, we got Brandon. Let me check out the chat before I move on. Rewrite that. No, thank you so much, y'all. Yes, thank you so much, Brenda. Yep, right now we're just reviewing. So no stress. This is just review of stuff we did before. And lastly, the last and ultimate last thing we left off on before y'all went to Thanksgiving break was this approximation method, which is called Riemann sums. Now, there was a process to this, and this right here is called a left Riemann sum because the upper left-hand corners of the rectangles are touching our graph. And this right here, we're trying to estimate the area under the curve from 1 to 3. And this right here is just an estimate. It's at 6.75. And it's not a perfect estimate because you still have these white space under the curve that we didn't take into account yet. So it's not a perfect estimate. It's just a way to make an estimate. And today we're going to explore how to make our estimate more perfect after we talk about the right-hand Riemann sum. So this is a recap from last time. All right, recaps. All right, let's jump into today's stuff though. So today's stuff, this is where you start our notes, everybody. This is the title. We're going to be talking about another kind of Riemann sum. It's called a right endpoint rectangle. And you want to also go ahead and copy down this graph. This is your right endpoint rectangles. Notice how this looks a little bit different from the left-hand one. Like now it looks like the rectangles are going over our curve a bit. I also want you to notice as you're sketching this down, the upper right-hand corner of the graph, the upper right-hand corner of our rectangle is touching our curve. So that's what makes this a right endpoint rectangle, because that upper right-hand corner is touching the graph, it's touching the curve. So let me let y'all sketch that out. And again, pay attention that it's not going to be perfect. So what I mean by that is like right here, this first rectangle, it's like a little bit above 2. Second rectangle is perfectly at 4. Third rectangle is going to be a little bit above 6. And this last rectangle is exactly at 9. So just be aware when you're making that sketch that some of these rectangles are going to be decimal approximation heights. All right, let me sketch that down. Yay, we got Marcella. By the way, if somebody came in and I didn't say you're here, let me know so I can make sure you're here. I could also repeat who I have absent. Here's who I have absent though, just to double check. So I don't have Denise. I don't have Miles Ford. I don't have Carlos. I don't have Risha. And I don't have Salia. Now we have Risha though, y'all. Yay. So that's who I'm missing now. All right, so cool. I hope y'all got your sketch down. And yes, perfect. All right, let's go ahead and type the rest of the stuff we need. So the next part of this is notice that the base width of each rectangle in this case is still 0.5. So what I mean by still is when we did the left endpoint rectangles, we again made our widths 0.5. This one also has a width of 0.5. That means the base, like each rectangle, is growing by 0.5 each time. And they're all the same. So each one has a base of 0.5. That's something you want to notice. Next thing you want to notice is, I did point this out already, but these are called the right endpoint rectangles because the upper right-hand corner is touching our graph, it's touching our curve. Let me give you all some time to get down these 2 bullets, and then we're going to go ahead and revisit that process and how we calculate the areas. All right, cool. I hope y'all got this down. I was just right now trying to text some students and remind so I can make sure to reply to y'all. Okay, so let's go ahead and jump back into the process on calculating the area of these rectangles. And again, this process is called Riemann sums. So this is our graph again. You don't have to redraw it because you should have already sketched it. But we're going to go ahead and try to find the area of these rectangles here. And these right here at the bottom, these are just ways to label our endpoints. Can we stay on the slide a little bit more? Do you mean the last one, AJ? Yes, yes. Let me go ahead and go back, y'all. Sorry. There we go. Yep. And then yeah, totally feel free to screenshot. And as a heads up, I do have these slides on Google Classroom just in case as well, by the way, y'all. All right, y'all. Cool. Let's jump into the calculation phase now. Now, this is super related to what you were asked to do in asynchronous number 12. Again, if you haven't done asynchronous number 12 and you need support, jump into my office hours. They're tomorrow at 10 and they're Wednesday at 10 because I'm happy to help and it's something you want to know how to do for the mini final. Definitely. Okay, let's do this. All right, y'all. So the first rectangle I color coded in green. So I'm going to focus on finding the area of this first green rectangle. The the first upper right hand corner point right here, right, corresponds to the x value of 1.5. The reason for that is remember the widths of each rectangle, it's growing by 0.5. And if 1 is over there, that means 1 plus 0.5 is 1.5. So this right here corresponds to an x value of 1.5. That's going to be the first point we're going to use to find the first height. So in order to find the first height, what you got to do is you're going to take 1.5 and plug it into your function. Now the function, in case you forgot, I'm going to rewrite it right here. It's y equals x squared. That's our function. And we're taking our input and we're plugging it into our function to get the height. So this right here is our height. So the first rectangle, that green rectangle's height is 2.25. But remember, we don't just want the height, we want to find the area of that green rectangle. To find the area, you do base times height. And if we go to the side here to do some work, base is 0.5 times height, 2.25. If you use a calculator, you could use your phone. You should get that the area of this green part, this green rectangle, is 1.125 units squared. So that's the area. And I put units squared because we don't have units. So you could put that too, it's fine. So this is 1.125. First green rectangle. Now let me just pause here to see if anyone has any questions again about our process and what we're doing here. This is the area of the first green rectangle. All right. So if we're good with that first one, we're going to move on to the next rectangle. So the next rectangle's upper right hand corner corresponds to the x value of 2 perfectly right here. So then what I'm going to do is I'm going to take that 2 and I'm going to plug it into my function to find the height. And that's in red right here. This is the next rectangle. Notice how I take 2, I plug it into the function. My function is x squared, so 2 squared is going to be 4 as the height for the red rectangle right here. But again, we don't just want heights, we want area. So we're going to do base times height. The base is always 0.5. The new height is 4. 0.5 times 4. You could use a calculator, but you should get 2 units squared. Oh, I'm sorry. So would the 1.5 be the height or the width? The 1.5 is basically, it's not a width. So there was a question about this 1.5 here. It's not a width. It's basically just the next endpoint. That's all it represents. The width for all of these is 0.5. It wouldn't be the height nor the width. It's just the next endpoint that you use to plug in. So the widths are going to be 0.5. The heights are what you get after you plug in those endpoints into your function. All right, so that's the first two, and we got 2 more to go. Again, I'm going to color code it so it's easier for you to follow what I'm doing. So as you can see in green is the area of the green rectangle, and red is the area of the red rectangle. So this one we got an area of 2. Now let's move on. Next rectangle is in blue right here. Now, in order to figure out which endpoint to plug in, like what X value do I plug in, you have to identify the upper right-hand corner is right here. You're going to trace it down to your graph, and you're going to notice that because this is growing by 0.5 and it's right between 2 and 3, this X value is 2.5. The 2.5 is not a width. That's just the next endpoint that I'm going to use to plug into my function. So I'm going to again repeat the process. I'm going to plug in 2.5 into my function like so. And if you use a calculator or your phone, 2.5 times 2.5 is 6.25. So that's the height of the blue rectangle. And again, this is just the height. To get the actual area, we're going to multiply by the base, which in all of these is just 0.5. And then when you do that multiplication, if you double check, y'all can double check this, but you should get 3.125 for the area of the blue rectangle. And then I got a good question right here in the chat. How do you find the height again? You find the height by first identifying where the upper right-hand corner is at. So step 1 is I find where the upper right-hand corner is at. Then I trace down to my x-axis and I identify what endpoint that is. This first one, the endpoint was 1.5. So then after you identify the correct input, you take 1.5 and you plug it into the function right here. And that's corresponded to right here. And this is how you find the heights. And I wrote down height right here. So these is how you find the heights. You're plugging in the endpoint into your function. In this case, this function is nice because it's just x squared. It's very easy to just plug in and square. Sometimes you might get a different function though. All right, so the area of the blue one is going to be 3.125. Now we got to do the last area. So the last area, it's going to be color coded in purple. So again, let me also verbalize the steps that I'm doing here. So step 1, I'm going to identify where the upper right-hand corner is. Step 2, I'm going to trace down to the x-axis and figure out what the endpoint is. The endpoint here is 3. Then the next step, step 3, I guess, is going to be I take 3 and I'm going to plug it into my function that's given to me. In this case, we're given that the function is x squared. So I'm going to go right here and I'm going to plug in 3 in for my x squared right here. So 3 squared, that's 3 times 3 is 9. This is the height of the purple rectangle. Once you have your height, you're going to multiply it by the base width. And then we know that the base width is 0.5, and that's going to be right here in purple when I calculate this here area. So in purple, we get that the area is 4.5. Cool. And let me know if anyone has any questions again about the process so far. But so far we found all the areas. So now what we got to do is just add up all these areas so we could get an estimate of the area under the curve. Because that's our goal. That's what we want to do. That's why we're doing this, trying to estimate the area under the curve. But I do want you to pay attention that these right endpoint rectangles are kind of going over our line though. So it's kind of going to be like an overestimate right here. But if I add up all these areas, right, I should get 10.75 units squared. So that's our right endpoint rectangle estimation. And some questions to think about right here, something to think about is the sum greater than or equal to the actual area? And I think I kind of said some of it. And how can we use this process called Riemann sums, that's the process of drawing these rectangles, to make a better approximation? So that's something to think about right now. You don't have to answer it because we're going to have a participation section right now. But let me just pause here for questions and for y'all to get down the work, picture, and the visuals. All right, I hope you all got this down. I hope you are copying it down along with me, and or take a screenshot, and also the slides are on Google Classroom as well. But I'm gonna jump us into our first participation check, which is this. So let me show you. Let me go ahead and clear my screen. So the participation point right here is going to have you take a look at the estimation we did for the left, and then it's going to have you look at the estimation for the right. So let me first put the link in the chat. Again, you want to either put your name or initials if you want your credit, name or initials. I'll be entering in the credit right after class today. I like to just quickly get the grades in, so that y'all know where you're at as far as the class is concerned. So right here for you, what I have is the screenshots for both the right Riemann sum estimate and the left Riemann sum estimate. For the right-hand side estimate, we got an area estimate of 10.75. And for this one, we got 6.75. This was from Thursday before the break. Yes, it's been a while since we did this. I want you to notice how they look different first off, how the area estimate is different. But here's the question. Which one would you use to make an estimation of the area under the curve? What's the best method to approximate the area, the left or the right? And how can we use Riemann sums to make an even better approximation than we have here? Like what's something better we could do to approximate the area under the curve? And then I even put right here, if stuck. So let's say you're stuck on you're kind of lost. Go ahead and just put a notice or wonder, and that will be your credit. That's totally fine. All right, we got 13 people in here. So we got AJ, Brenda, we got Sincere, Gerardo, both Jasmines are in, Risha's in, Zion, Danny, Gabe, Rebecca, Miles, Sam, and Leon. Again, if you're not in here, you make sure you're in here. Let's see, we got more. We got CJ. Definitely want to be in here. Either put your name or your initials for your credit. This is there's no way you could be wrong here, because if you're stuck, you could go ahead and put a notice or wonder. Great, we got 18 people on the document. We're missing 4 more. If your name is not up here, make sure you join with us. Join us on the document. Got 19 of us in. Okay, we got more. We got 21 now. Yay. It's awesome. All right, we got, yep, yep. Let's make sure we're typing our name or initials on there. We're putting down our thoughts. Again, what is the best method to estimate the area under the curve? And would you use the left or the right? And any ideas on how we can make a better approximation? Because we're going to try to make this even better because they're not perfect. The estimates are not perfect. Give you all some time to type some stuff out. I notice they're still writing a bit. Have about 1 more minute and we're going to take a look at some of your ideas, some of your thoughts. All right, so I'm going to go ahead and point out some thoughts and some ideas here that are worth noting. First off, they're all important because they're all our thoughts. But just some things that's going to lead us into the next thing. So first off, I do want to say that the left Riemann also has the upper left-hand corners touching the graph. The right Riemann is when the upper right-hand corners are touching the graph. So they're both like the same kind of method, but it just depends on which corner is touching the graph, just to kind of like remind you of that. And the process for both of these is the same. It's not like one of them is easier. They're both the same process. It just depends like which one are you going to use to make your estimate. All right. So we have a bunch of rights. I noticed that most of you are preferring the rights, and I'm also just wondering if it's also because we just did a right one and the left one we did quite long ago, and it feels like the right Riemann is like more fresh in our minds, but that's cool. So I feel like the right Riemann, because I have a better understanding, I noticed that the line going through the bars are colored. All right. All right, and I think I saw an idea here from Danny. I noticed that one is an underestimate, and I think he means the left is an underestimate because you have these white spaces that you're not taking into account, and the other is an overestimate. Notice that instead of having white spaces, these rectangles are going above our curve, which is basically an overestimate of the area. And then here's an idea. I believe that if you do both of these, add them together and then divide by 2, you get a more reasonable answer. But then Danny says he doesn't care either which one to use because they're the same. All right. This one says the right Riemann, Zion says, is better because it takes into account the white spots. And so because it does that, it allows you to have better units to get the sum of a better all unit. All right, let's see. All right, so Sam says again he'd use the right because there isn't anything missing. So as in there's no white spots. There is extra, but I think it would be better approximation because it takes into account all of the space, not just some of it. All right, that's pretty reasonable. All right, let's see what other ideas we have. And yep, yeah, some rectangles are going over, some are going under. And then to use the vocabulary, we would say overestimate versus underestimate. And then, so AJ says, I feel like the left Riemann is the best to get the closest estimation. You just have to insert the endpoints into the function to find the areas. All right, doesn't matter. So RG says, doesn't really matter which one because they're both estimation methods. So a lot of us are preferring the right Riemann. Oh, okay, let's see this one. So Sincere has an idea. I'm just pointing out to see what ideas we're coming up with as well. So Sincere says, I think the one on the right is better, but I would use both by using the right's area estimate, then subtracting by the left estimate, then divide the sum by 2 and add it on the left side. So there's like a process there. Ooh, okay. So this was a new idea. The left, because it's better to have an under than to go over of what you have. I mean, I would totally agree with that, especially when it comes to money. I definitely would want to underestimate rather than overestimate how much I have, because then you're going to overspend. I don't know. For some reason, I think about money when I think about this. All right. And for those of you who are not done, like I noticed some just put your name, make sure you put in your thoughts there for your credit today, and also finish your sentence if you haven't yet. So yeah, so we're gonna explore. So I noticed most of you are leaning towards the right, Riemann sum. Some of you have offered some ideas on how to kind of make up for the fact that one is an under and one is an over. So we're gonna actually talk about how we can use Riemann sums to make a better estimate. So what's the best way? All right, so let's go back into this. Okay. And this is going to be our second round of participation. So I'm going to jump over to this slide here. So this is what I'm going to do. In a second, I'm going to show you first this tool, and then we're going to jump into our participation once again. So that's going to be part 2. So you want to do both for your full credit. So let me show you this tool. And this tool, by the way, is in your big ideas packet, and you're also free to use it if you want to for your mini final for the future. So right here, what I have for you is the function that we were working with, f of x equals x squared. And this right here is a cool tool. It does the Riemann sums for you. What we're looking at right here is a left Riemann sum. The reason for that is because the upper left-hand corners are touching the graph. So this is a left Riemann sum. And this tool is pretty cool because if you scroll down a bit, right here, to find the area is right here. And it tells us, and you could notice how sigma notation has something to do with it, but we didn't really get to talk about it. Don't worry about it. It's right here, 6.75. That's the area that we did calculate. And this tool actually calculates the area for you. So it is a useful tool. If you want to do a right Riemann sum, I just have to put 1 right here. And there's your right hand Riemann sum. Notice how it goes over. So the question is, how can we make a better estimate? So I'm going to actually start with the left-hand sum. So I'm going to put 0. I want to start with the left. And I want to show you something. So originally we had, I think this represents number of rectangles. Yes, 4 rectangles. So what if I make less rectangles? What happens to my approximation? So this is less. This is 3 rectangles. This is 2. And then this is 1. Literally, if I try just make 1, it'll look like this. So As I'm using less rectangles, is my approximation getting better or worse of the area under the curve? That's just something to think about.
More. Wait, do we share out loud?
Go
Like,
ahead. Okay.
okay. More is better, right?
Okay. So you're saying more is better. So if I go less, it's pretty bad.
Yeah.
All right. So if we say more is better, let's go ahead and take your idea. So I'm going to add more. So let's do 5, 6. We got 7, 8. This is 10 right here. So remember, to get the perfect estimate, all the white spot below the curve should be filled up. Let's do, I don't know, let's do 20. 20 rectangles. Imagine you all have to calculate 20 rectangle areas. That's a lot of handwork. But luckily this tool does it. So when I have 20 rectangles, it says the area is about 8.27, which makes sense. The area should go up as long as those white spots are getting filled out. All right, let's try, I don't know, let's try 40. And wow, like if I was to zoom out here, it looks like it's completely shaded in that full area under the curve, doesn't it? But of course, if I zoom in, you still got very small little triangles there. Still some white space under the curve. So I'm gonna go ahead and just take this idea further and let's just say 100. Let's go all the way to the maximum this tool can do. And let me zoom in. So wow, 100 rectangles. Imagine calculating the area of 100 of these. Again, this looks like it's almost all shaded in. But of course, like if you zoom in a bit, you still have very miniature triangles. The area isn't fully taking into account of, but this is pretty darn good estimate right here. If you were to have done 100 and then calculate that by hand, I can already stress estimating 20. Don't get me started with 100. So don't worry, you won't ever be asked to do 100. But that's why this tool is useful, because when you're in upper like level mathematics in college and stuff, you're not going to be asked to do by hand. That's why we have computers, calculators. You should understand the basic ones, right? But then once you get to like 1,000 rectangles, you could use technology to do that work for you. So that's 100 rectangles with a left, right? Left endpoint. Let me go back to 4. Back to 4 rectangles. And let me show you if it's a right Riemann. So again, this is when it was an overestimate. Let's try the same process. I'm going to again do 100 rectangles. Boom, 100. This is 100 right here. Now if I zoom in, again, wait, first off, if I zoom out, the area looks fully shaded in first off. It looks really nice. But of course, you kind of see teeny little triangles kind of popping up above the curve. So it's still pretty, I mean, it's a pretty good estimate, but it's just going to be a very, very slight overestimate. We have a little bit going over. And this area approximation is about 8.7468. Yeah, thank God for computers. It's true, because that's why a lot of this technical work can be done by computers. But this is just to show you all how can we use Riemann sums to get a better estimate. And if we could create a program that does the calculations for us, it makes life pretty easy. Just like this Desmos, it's just like a program. You're just typing in what you want the Desmos to do, and it'll do it for you. This right here is calculating the area for you. Okay, so that was this tool. I went ahead and talked about it so that you can go ahead and put your ideas in the second participation. So let me go ahead and pop this open. So this is part 2, participation. Let me put this in the chat. All right, everyone, part 2. You want to make sure you're on this doc. You put your name or initials, and let's put some ideas down. So in this participation doc, in your own words, describe what happened when we added more rectangles to approximate the area under the curve. Would you create more rectangles with a right or left, and explain why? So I both showed you left and right. I did start with a left. And again, if you're struggling, you could just put a notice or wonder on what happened when we just did this Desmos activity. I also linked the Desmos activity for you here so you could explore it on your own. And again, you could use this tool for any of your assignments as well. All right. Great. We have 13 of us in. We have Brenda, we have Danny, Jasmine with a Z, Rosario, Sam. We got Cyan. The other Jasmine's here. We have Anonymous Fox, Gerardo, CJ, Risha, AJ, Gabe, Rebecca, and Brandon. So we have 17 so far. If I didn't say your name, please make sure you jump in on here so you could get your credit. For Shirley, this is easy way to get credit because this is just about your thoughts and ideas. How would you use this tool, right? To make some approximations under curves. And or would you still use a right or left, depending on what you saw right now? All right, we have 18 of us in. Great, great. Thank you for joining us in here. We're missing likes. We're still missing like a good 5 of y'all. Make sure you get in there. I don't want to give an NC for the missing credit. Great, great. We got more. Got 19 of us in. All right, let's put down our thoughts. Let me get my timer. Take about a minute there and we'll take a look at what y'all are thinking about. All right. Make sure you're if you're still typing out your idea, go ahead and keep typing. I'm gonna go ahead and just point out some things. I think you kept the same amount of rectangles, but you just have more numbers to calculate. I think kept the same. So I know in the tool, when I was increasing n, I was actually increasing the amount of rectangles. So the amount of rectangles went up for this one here. All right, so here's an idea. I feel like adding more rectangles is helpful, regardless if you're using either left or right. At least that's what I believe. I think the rectangles are the only thing that changes. Adding more rectangles resulted in a more accurate representation of the space captured by the graph. Just looking at it, the graph looks more full and correct, and the second one looks more correct / normal to me. Okay. So the second one, I think being right, Ramon, looks more full. Okay, yes, I love this. Adding more rectangles resulted in less white space and therefore more accurate result. When you add more rectangles, it becomes a closer approximation. However, it did go over a little. I will still use the right Ramon. Perfect. Okay, so a lot of you are like, the right Ramon feels like even odor estimating is the right option. The more rectangles, the better. Correct. I mean, that is our big idea. The more rectangles we use, the even better our approximation. Okay, so with the left, you see white spaces. And then with the right hand, you don't really have those white spaces you have to worry about. All right, depending on the situation, but if I had to choose, I'd do an underestimate and make as many rectangles as possible. I guess when you add more rectangles into the graph, the approximation starts to become more precise. Yes. Okay, I like this, Rebecca. So Rebecca says, I would use the left because it's asking for the approximation under the curve and not over. So the left one would make more sense. Ooh, okay. I like that. Depending on different graphs, I'd overestimate because it's like that. You'll have more rectangles that you have. All right, y'all. These are amazing. And I like how many of you actually hit our big ideas. Just make sure if you're type out your ideas if it's blank. Because right after class, I do add the credit. Again, you could put a notice and wonder if you're stuck, but please make sure you add in a contribution so I could give your credit. Awesome. Thank you so much, y'all, for sharing your ideas. Some of you are adding more information. I can't wait to read this. All right, let's go ahead and get back into our slides so we could synthesize the big ideas. Now, this is something you want to write down, and then we're going to have our checkout. So after all of these investigations, you want to write this down. And of course, you should have write down the right Riemann sum. So here are the big ideas. Some of you already mentioned it. So number one, Riemann sums are used to approximate areas under curves. That's a big idea. And it's up to you to choose left or right Riemann sums to create the better estimate, increasing versus decreasing. So that's one big idea. Let's go ahead and write that down. Super important. And it's going to show up in your big ideas packet. Oh, we got something in the chat. Yes, you want to write this down. And then, by the way, it's on Google Classroom too, in case you don't have a chance to get this down. But yes, you want to write down these big ideas so that it could, stick as well. All right, the next big idea, the smaller the rectangle width, the better your approximation. So I don't know if y'all noticed that, but when I was increasing the amount of rectangles, the rectangle widths got smaller and smaller and smaller. So the width, as it means the base of the rectangles, were getting very, very tiny. So the smaller the width, the better your approximation when you're finding the area under a curve. So that's a huge, big idea. Then we got one more bullet, and then we're going to jump into our checkout. All right. The last important big idea is basically the difference between the left and the right Riemann sums is based on either using the left or right endpoint of the rectangle and the upper left-hand corner or the upper right-hand corner of the rectangles that touch your curve. So that's the only difference between the two. It's whether the upper left-hand corner is touching the curve or whether the upper right-hand corner is touching the curve. So sometimes the right gives you an overestimate or sometimes it gives you an under. And we're going to talk a little bit more about that in our next class on Wednesday. We're going to look at when, because maybe some of you are thinking right now that the right always gives you an overestimate. It's not always the case, actually. So we're going to take a look at the difference between left and right in our next class. But overall, these are our big ideas, and we're going to be jumping into our checkout right now. Let me let you all get that last bullet. All right, y'all. I'm going to go ahead and take us into our checkout. And the checkout, don't worry if you're still copying this down, it has a screenshot of it. So, which big idea from today's lesson is the most challenging is our checkout question. And we could say one, two, or three, or you could actually type out the big idea. That's fine. So, that's one, two, and three. So, what big idea is the most challenging? All right, we have number two. The smaller the width, the better. That's true. I mean, I would say that's challenging to calculate because smaller width means you have enormous amount of rectangles. All right, and we have some threes. So the difference between the left and the right. All right, we got two and three so far. Okay. Two and threes. Yeah, the difference between the light or the red or in the left. Oh yeah, this one here has something different. Three if I had to choose something. So I didn't talk about sigma, so I took the incorrect screenshot. But yeah, two or three. That's good. All right, so number one seems okay. Riemann sums are used to approximate areas. All right, awesome. And then number three. All right, y'all. Thank you so much for sharing. You know what's challenging from today's big ideas. We're gonna close this up a bit on Wednesday, and then we're gonna soon get started on our mini final because our module's almost done. All right, everybody. Y'all have a great afternoon. I'll see you all on Wednesday. Don't forget to get your homework in for Tuesday, y'all. It's a big ideas. It's a good one. It's an easy one. All right. Bye, everybody.
Alright then.
Bye. Bye, CJ. Make sure y'all come to office hours if y'all need support. Bye, everybody. Yup. Be safe. Thank you. All right. Let me go ahead and end. Bye, y'all.